Right. Okay, so today we're going to discuss one of the final topics of the lectures, which is finite temperature. This is going to be the main topic of today, but we have to finish some unfinished business from yesterday, which was the discussion of the derivation of the Weyl anomaly from holographic renormalization. So we will deal with this in the first about 20 minutes or so, and then we'll switch and go to the next topic. So yesterday, I motivated the derivation of this counterterm action. If we start in d-dimensional, d plus one dimensional ADS, and in particular here I wrote the coefficients and the numbers for d equal 4, so that we don't have to say if d is even, if d is odd. Now we are in d equal 4. And this was the counterterm, which is necessary in order to remove the divergences of the pure gravitational plus Gibbons-Hawking action. And here, as I was explaining yesterday, the quantities are all computed with the induced metric on an arbitrary boundary at an arbitrary distance, small distance epsilon from infinity, which is z equal to 0. So there are some terms which contain power law divergences if you expand them out in terms of inverse powers of epsilon. And then there is the logarithmic term. So this is all it's needed to make the full action finite. So the use that we're going to make today of this action is to derive the holographic version of the anomaly in the trace of the energy momentum tensor. So T, trace of the energy momentum tensor in the dual field theory, is some anomaly. I just write A, something different from 0. And I will derive that from holography, and then I will make contact with the discussion in field theory, which I know that I suppose that it's not going to be discussed in the CFT lectures, so I'm just going to briefly explain what is the expectation in the field theory. For some, for a coincidence, I mean, not for any particular reason, the metric that I'm going to use here is slightly different from the one I used earlier, but the difference is really trivial. So I define the coordinate rho to be just z squared. I could rewrite everything in terms of z, but I was not bothered to do the change of coordinates in my formula. So we have the metric, which is some d rho squared times 4 rho squared, and 1 over rho. And our Pfefferman-Graham coordinate system here is given by rho and x, dxi, dxj. So since we are interested in anomaly in the Weyl transformation in the field theory, then we have to perform a Weyl transformation on our effective action, which is given by the on-shell action, and see how it transforms under this transformation, right? And if it's non-zero, we will obtain the anomaly. So we have to implement in the bulk what is a Weyl transformation of the boundary. So we have to find a diffeomorphism. Well, we have to say what it is. This was studied by Penrose, Brown, and Hernot. So this is called PBH diffeomorphism. Which is a diffeomorphism in the full bulk, which corresponds to a Weyl transformation at the boundary. So this involves a change of the radial coordinates, which can be written in this form, 1 minus 2 sigma, where sigma is an arbitrary function of the coordinates on a given radial slice, x, and the coordinates themselves are changed as follows. some shift. There are some conditions on this vector AI that then give an explicit expression for this in terms of the metric itself and sigma. So rho hat is some integration variable. Sigma of x. And then, if you perform this diffeomorphism, then the metric on the boundary is changed by the following shift. So in particular, notice that as rho goes to 0, so it's approaching the boundary, AI goes to 0 just by construction. And at the boundary, we obtain the transformation that we wanted. We have that Gij is simply shifted by sigma multiplied by sigma, which is the infinitesimal version, if you take sigma small, of this Weyl transformation. Right. So equivalently, or put it very simply, the transformation of Gij is 2 sigma Gij. So this was also explained yesterday at the beginning of the CFT lectures. Yeah?
How can sigma and AI be functions of the transform coordinates? There shouldn't be a dash there in AI for a dash, right? You need to know how to find...
It's just written in the inverse. I mean, it's just written in the inverse. Right. It's given the old coordinates in terms of the new, or you could put primes on the other side. It's the same. Okay, so that's the transformation that we need. It's not important that you check the details at this level now. The important thing for you to understand is that this is a diffeomorphism in the bulk. And by construction, the bulk action is invariant under diffeomorphism. And it reduces exactly to a Weyl transformation at the boundary, which is the transformation that we want to implement. So if we want to check how our action transforms, then we perform this transformation, BH, on the bulk action plus the counter term action, right? Where the bulk is the initial bulk plus Gibbons-Hawking term, and the counter term is exactly that expression written there. But exactly for the reason which I mentioned, this is invariant under this transformation. So this is acting only on the counter term action. So let's write how it acts. So this is some d for x, d rho plus delta Gij on the counter term action, which if I put then explicitly what is delta Gij and what is delta rho. So let me just put in different color here. This is just 2 sigma Gij, and delta rho I I read from there, it's -2 sigma times rho. Okay, so I can take this 2 sigma in front. Sigma is here always a function of x, so I can't really pull it out, the integral, but I can take it here. And then I have two different terms. But the important thing to say is that when you do this transformation, and remember here, rho is equal to epsilon, when you do this transformation, then you can see clearly from that expression there that all these terms are invariant. The first 2 terms are invariant under this term here, but the logarithmic term clearly picks up a non-zero transformation. The other term, well, it requires a bit of computation, so I leave that as an exercise, but one can check that there is no contribution from this term into the variation. So this one really picks up the logarithmic term. And with all the coefficients put back and with the details, then it turns out that the result of this transformation is 1/16 pi g 2L cube 1/8 Rij minus 1/24 R square. Right. So we calculated this from the effective action in ADS. And I'm going to come back to this G Newton in a second. But let me just say whether this is something surprising or interesting, or let's just make some comments on the field theory expectation. So on the field theory side, it is known, it was known from much before the ADS-CFT correspondence, that the trace of T generically in D equal 4, to be concrete, takes the following form with canonical normalization. Okay, where I4 and E4, I'm going to write for you explicitly, are some invariant. So I4 is Rijkl, Rijkl. This is the Riemann tensor contracted with itself, and this is the Ricci tensor contracted with itself, and there is a factor of 1/3 square. So in fact, these numbers here are not random numbers. They arise in this way because this is also equal to the square of the Weil tensor. But okay, let's not dwell on that too much. This is also another canonical invariant, is the Euler density, which is a topological invariant, and it is written by Rijkl, Rijkl. So it starts with the same object. Here has a -4, and here has a 1. Okay, so previous calculations that have nothing to do with this prove that this is the general expectation for. So here, what I mean by field theory, I mean general CFT. Right? So there is not even assumption of supersymmetry here in this formula. Oh, I deleted my anomaly. Okay. Sorry, I should have pulled out this. So if we compare the derivation of the anomaly here with this general expression here, then we learn two things. Okay, so we learn that A is equal to C, and also we learn another fact. We learn that A, which is equal to C, is equal to pi L cubed divided by 8G. Just by comparing the formula on the two sides, I will actually leave for you the algebra, the trivial algebra to check. If you set here A equal to C, then these invariants recombine, and they create exactly the term that appeared in the calculation of the holographic Wien anomaly. So that's this point. And we get this kind of a universal formula that any CFT in 4 dimensions with a holographic dual is then supposed to have an anomaly A, which is given up to these factors by the inverse Newton constant in 5 dimensions. So if we want to say a bit more about what is the value of this anomaly for some particular theory, for example, for n equal 4 Superyon-Mills, okay, it has been the main focus for most of these lectures, then we are really to specify what's G. And here, let me add a subscript to remind ourselves that this is the Newton constant in 5 dimensions. And as I perhaps have mentioned already, in the context of the near horizon limit of the de Bruijn, etc., the 5-dimensional Newton constant is related to the 10-dimensional Newton constant by a factor of the volume of the internal manifold. Let's take S5 for the moment, because that's the only thing which we have discussed. And there is also a dimensionful term, which is the radius to the power 5th of the sphere, or which is the same of ADS, where G Newton was given by, in 10 dimension, was given by, comes from string theory, as we did in the very first lectures, and it's given by this value, 2 pi to the 7th, ls to the 8th, and gs squared. Okay, so now you have all the ingredients that you need in order to compute. Well, maybe the other ingredient that I should remind you is the value of L to the 4th, so that you have really all the ingredients on the board. 2 pi to the 4 gs ls to the 4th, and sorry, ls without 4. Yeah. No, yes, ls to the 4. All right. Now you have all the ingredients. You just have to cook them together and do a little bit of algebra, which again I will not repeat here, since it's completely trivial. And then you get the following fact. Let me write this in this schematic form. So you get, first of all, that's easy to see if you trace this. So for example, for G5 here, you get 1 over L to the 5. So if you combine, you get L to the 8, and then you see that you have a n square. So n comes with the power 2, so you get n square. Then you get also, well, then you get some factors all these annoying pi's and 2, etc. And also the other thing to notice is that how the volume appears, right? So from here, G Newton has 1 over the volume. So because the formula contains 1 over G Newton, you would think that actually this is linear in the volume. But from this, where was that? Oh, sorry. That's why it didn't appear. There was a denominator here. Right? From this term here, you see that there is also 1 over volume square in the formula. So in the end, you get volume of S5 here. And when you put all the factors back in, then you have this famous, to some extent, formula, which then, if you simplify the factors of pi for S5, it reads like that. Okay, so since I'm really using S5 in an explicit way, and I've done the calculation in ADS5, then here the only thing that makes sense to compare is n equal 4 super Young-Mills. And in n equal 4 super Young-Mills, not surprisingly, you get that A is equal to C, equal to n squared over 4. This is the not surprising part. Perhaps the thing which was not totally expected is that there is also this factor. But of course, at leading order in n, this agrees exactly with the calculation in the gravity side. Yeah. Yeah. The best piece of evidence that it's SUN that I presented at these lectures is the fact that the Kaluza-Klein spectra match only for SUN, not for UN. That's the most concrete way to see that. Okay, so the agreement is obtained at leading order in and it's an exact agreement, exact meaning that this is 1/4 and this is also 1/4. Okay, so if here we obtain something that goes like n squared with some other factor, it wouldn't be really a great matching. This is much better because we can really match the factors perfectly. Okay, some remarks before we move on. The fact that we obtain A equal to C and the fact that this matches with what is true in n equal 4 super Young-Mills does not mean that any conformal field theory or even any supersymmetric conformal field theory necessarily has A equal to C. And indeed, there are many examples of supersymmetric conformal field theories in which A is not equal to C. But it is a feature of all the solutions which have a gravity dual with ADS5. Right? So that makes you appreciate that those are a subset of all the possible superconformal field theories. Another remark which I wanted to make is that this Weyl anomaly here, as you can see explicitly from the computations on both sides, does not depend on couplings. And that's a general feature of the anomaly. So it's a very robust quantity that even in other more general situations where you have other examples of dualities, for example, with the reduced supersymmetry, for example, n equal 1, then it's also it's typically a quantity that you would like to compare on the two sides. Remember, I was making these comments about the dimension of operators which are not chiral primary operators, which get renormalized, so they are very hard to compare on the two sides, whereas the chiral primary operators have dimensions which are locked with our symmetry, are charges, and therefore they are robust quantities. So, in fact, the central charges are similarly robust quantities to compute, and in supersymmetric theories, maybe I will say something more tomorrow, they are indeed related to these R charges as well. So, in a sense, they're also locked by the R symmetries. In the case of n equal 1, well, okay, well, let's save this for tomorrow if I get to speak a bit more. What I want to say here, and that's easy to say without a lot of discussion, is that suppose that you didn't have S5, then the full computation still goes through completely. In particular, this part of the computation has nothing to do with the internal part of the solution. It has only to do with ADS5. So the result would be just pi cube n square divided by the volume of whatever manifold replaces S5. Okay. So tomorrow I'm planning to talk, depending on how much time remains, a little bit of replacing S5 with some other manifolds, and we can anticipate that that would be the formula for A and C. Okay, so that took slightly longer than what I was expecting, but more or less it's fine. So we can go on to the next topic of the finite temperature. Sure.
Did you say that maybe I misunderstood? There is some theories we can define duality, but there is some theories we cannot duality.
In some sense, yes, that's what I said. What I said can be rephrased by saying that there are some conformal field theories, even some supersymmetric conformal field theories, which are not dual. They cannot be dual. I mean, it's impossible to be dual to anti-de Sitter five-dimensional anti-de Sitter solutions in supergravity.
But in principle, we are constructing the duality on the operator level, not the theory level. Like whatever we have in the bulk, we can map that operator or observable to boundary, and then we have propagator.
No, it's not like that you can take whatever you want and always construct a dual. It doesn't work like that. I mean, the space of all the possible conformal field theories is much bigger than the space of or it does not coincide with the space of anti-de Sitter 5 solutions. Or I could say anti-de Sitter in general in any dimension. I mean, this is just proved by evidence, by example. There are examples which, for example, do not have A equals C, so cannot have a gravity dual in ADS5. Sometimes you can compute corrections, and then you can argue that you can enlarge a little bit the number of solutions which have a field theory dual. But we can discuss later. I'm not sure exactly what is your question. Other questions? So more broadly, what I'm about to talk about is, I would present it in this way, as possible deformations of ADS5 plus S5, and also corresponding to possible deformations of n equal 4 superunion mills. Now, the word deformations here is in a loose sense. It's not that you're taking the solution necessarily and make a small perturbation of it. It's rather how you can replace something, for example, replace S5 with some other manifold. So if you have we started with ADS5 cross S5, which I claim was the main example of the ADS50 correspondence. The question is, how can we, starting from this structure and the fact that this is dual to n equal 4, what can we do to deform this? And, well, two things come to mind immediately, obviously from this product form, which are either we deform ADS5, keeping S5, or we deform S5, keeping ADS5. So here, as I said, deform, I will put in quote marks. So these are two main possible things that you can imagine, but you are not limited to this. You can have combination, you can do both simultaneously at the same time. Of course, there is no point in explaining to you everything deformed at once. So I will discuss today just deformations of the ADS5 or some particular type, keeping this basically irrelevant factor. And tomorrow I want to say something about replacing that. But there are much more dramatic deformations that you can do. You can have things which do not have a product structure, or you can have things which do not have any ADS factor anywhere, not even asymptotically. So those types of solutions are less understood from the holographic point of view, but there are nevertheless quite famous examples that have been studied for many years. One that I can mention here is the Klebanov-Strasser solution, dual to the cascade and so on. So those have a holographic interpretation, although there is no asymptotic ADS5 anywhere in the solution. Okay, so what I'm going to do here is to now focus on this part. And the type of deformation which I want to discuss today is one which, I should say, just don't spread the word, but I don't like particularly. But it's still interesting. Okay, so it's a supersymmetry breaking. But it's some breaking done not randomly, just by taking a hammer and breaking that, but done by introducing a finite temperature. Here, finite means different from zero, as in the jargon. So, just one word about what do you do in the field theory to have finite temperature. So how you heat up your field theory. You do that, for example, in the path integral formalism by going to Euclidean. So first go to Euclidean, and secondly compactify time. Phi Euclidean, so T Euclidean, making this periodic with some radius, some periodicity beta, and the partition function then is written formally as a function of this beta. E stands for Euclidean. You have some huge path integral over all the field configurations. You have your Euclidean action, depending on the fields. And then the rules of the books in the Feynman formalism tell us that this is the trace of e to the minus beta h, where h is the Hamiltonian of the system, right? So this is really the partition function of statistical mechanics. Then you have to specify, since this is now a compact direction, and then all the fields will have to go around this circle, then you have to specify the boundary conditions for this, for every field. So, for example, for the bosons, so for the bosons, phi, then phi of x at Euclidean time is equal to phi of x at Euclidean time plus beta. Right? So they are periodic, all the bosons, whereas the fermions have to pick up a minus sign, so they are antiperiodic, and that breaks supersymmetry generically. Okay, so supersymmetry is broken by the temperature, as also intuitively you may imagine introducing some temperature in a system it's going to take you away from the vacuum, and therefore supersymmetry is going to be broken. Now, this same basic trick here, or recipe, allows you to go at finite temperature in the gravity side. So there is a parallel in the two sides. So this was in field theory. So this was in QFT. And in gravity, in general, we do the same. So we go to Euclidean by doing a weak rotation. T goes into IT, and then compactify this time direction. So there is not much more to say here, so do the same. And let's see how this works in practice. And to see that, we go back to the simplest solution, in fact, the first solution that was ever found in GR. And that's the Schwarzschild black hole. So now here I have to copy how it's spelled. Black hole. Right? So some of you will complain that this has nothing to do with ADS, but I'm just using this as a preliminary exercise, because I'm not sure that you have seen this before. Certainly not at these lectures, at this school. So we write the line element, very nice and simple. Everything is physical here. This is something which is more than 100 years old, surprisingly. So back then, everything was four-dimensional. 2mg dt square plus dr square 1 minus 2 mg over r plus r square and the round sphere on the round metric on the two sphere. So I can do the weak rotation on the same line. If I take t that goes into minus I, let's call it tau, then this becomes plus and this becomes tau. Okay, so this is now the Euclidean solution. Now the Lorentzian solution, being a black hole, obviously had the horizon, and where, for example, the Killing vector d by dt vanishes, and it is a horizon with a finite area given by some finite radius at which this function vanishes, and with just the topology of the sphere. In fact, the horizon, let's call it r star, is located at 2 mg. Okay. So now, if we are in Euclidean, there is no horizon. The notion of horizon doesn't make sense. So what do we have to do instead in Euclidean? So the rules are that we have to check that this solution is non-singular. Now, since it was not singular even before in Lorentzian, that means that all the curvature invariants are finite and well behaved. So there is no curvature singularity. So what do I have to check really? I have to check that there are no conical singularities, which are not detected by the curvature. Okay. So roughly speaking, you see that when the coordinate r goes to this limiting value, then, well, this function here blows up, and this goes to 0. But since you cannot go past that, in this case, so the space has to terminate, and it has to terminate in a smooth way. So r here, as the name suggests, is a radial coordinate, and since now tau is periodic, so tau here, you have to remember that tau is periodic with period beta, then this part of the metric, this part of the space, there's nothing bad with this, because this is some just finite value, and this is the round 2 sphere. So you are really to worry about this part. And you see that because this is periodic, this is like polar coordinates in a plane. Right, so roughly speaking, you have tau, and you have some r. So everything is fine, except it's not clear what happens at this value here, right? Like in the plane, at the point r equal to 0, the angular coordinate is not well defined. Doesn't make sense. So you have to check it by changing coordinates, for example, by going to Cartesian coordinates. So that's the idea. So we say that in rho r tau, the space looks like, so we suspect that it may be just R2 in polar coordinates, or some coordinates similar to polar, and we want to establish whether this is actually true or not. And to do that, it is convenient to change coordinates. So change coordinates and define some rho square to be equal to r minus 2mg, so that this looks more similar to the radial coordinate, because it goes now between infinity and 0. And look at the metric itself near to this rho equal to 0. So near rho going to 0, the metric looks like that. So I just need to consider the first expansion terms in the Taylor series around rho equal to 0. So we get 1 over r star rho square d tau square plus 4 r star d rho square. That's nice. Plus r star square ds square of s2. That's much similar to polar coordinates. You see that this goes really like the dr square term, and then there is this rho square d tau square. So in fact, to discuss that, we can simply pull out this factor of 4r star. So if I pull this out, I get 4r star here, and then I have 4r star here, 4r star here, right. And then I can simplify that. So the metric here inside the parentheses is now some d rho square plus d tau square something. So I can even do, let me do this again in front of you. I rewrite this simple term by putting everything inside the square. So I write this like d tau over 2. So d tau over 2 r star. Okay, so I'm done now, because really this is the metric locally of polar coordinates, and all I have to declare in order for this to be well defined is that this angular coordinate, so tau over 2r star, has to be 2 pi periodic. Right? Has to be 2 pi, not something else, not 3 pi or something else, because this is the coordinate on the plane. Right? And the plane, if you go around once, is 2 pi. Okay, so that means that beta, so the periodicity here, is then fixed to be 8 pi mg. But beta is nothing but 1 over t. Okay, so that gives the temperature at which the black hole is in this Euclidean quantum gravity approach. And I can also say something else about black holes, which is very general and can be derived trivially in the case of the Schwarzschild black hole. And it's the famous relation between the entropy and the area by Bekenstein and Hawking. So if you consider the first law of thermodynamics, where this is now the energy, right? But for our black hole, the only energy that is present is its mass, for the Schwarzschild. So from this law, we get that S is equal to some integral of 1 over t dm. And so I have just to integrate that. And of course, I cannot pull it out t here and get something wrong, because I know that t is inversely proportional to the mass itself. So I have to do this integral. And if I do the integral, I get 4 pi g m squared, which you can check by doing a trivial exercise, that's equal to the area of the horizon divided by 4g. So I've given you a one-line super fast derivation of the Bekenstein-Hawking area law, and this is true in very general situations with much more general solutions. Okay, so this was just an intermezzo about black holes, but I will use both this temperature knowledge and this technique, how to fix the temperature of a black hole, and this area law in situations which are relevant for the ADS-CFT correspondence. This, as I commented, is not relevant because it's not asymptotically ADS. So what I'm going to do now is to combine ADS with this knowledge of black holes. In other words, I'm going to consider a black hole in ADS, or said in another way, an asymptotically ADS black hole. And I will do this in two different big families, and then I will make some various modifications in various cases. But the two main distinctions are in terms of which coordinates you consider ADS, so the global structure. So I will consider black holes in ADS, both time permitting, but I think time will permit it, both in Poincaré and in global coordinates. And there will be some interesting physics associated to both these. So let's, yeah, this is a very beautiful solution. I really like it. Okay, so let's postpone this for after the break, of course, and start with discussing the Poincaré coordinates. And to do that, I'll go back, and this is perhaps the second of 3 times that we'll do that. Go back to the brain solution. So go back to D3 brain solution. And make explicit a comment which I made at the time. So it may have escaped you because I didn't write any formula, but I mentioned that the supersymmetric D3 brane solution admits a canonical type of deformation, a simple deformation, that breaks supersymmetry and corresponds, in fact, to some finite temperature. So I will write the deformation, and then we will verify and check that actually corresponds to finite temperature. So this is the deformation. So in the very same coordinates that I used back last week, we have the harmonic function h of r, and then we have a new function, f of r, that appears in front of dt squared. The x squared is the spatial part, and you have h to the power and half, the r squared over f of r plus r squared ds squared. And today we don't deform S5, so we just copy it as 5. Now h is harmonic function as before, so it's completely untouched, with L being exactly the same function of factors of n, gs, ls, etc. And f is a function of r, which is in fact another harmonic function, but it has crucially a minus sign here. So there is some constant here, which I'm going just to call it r star for obvious reasons that will become obvious in a second, to the power 4. So if you take r star here to 0, which because it's a free parameter, you can certainly take it to 0, then f becomes equal to 1, and you are back to the supersymmetric D3 brane solution. So this is really a deformation in the sense that I said before. In fact, you can even take this to be small, right? Because you can take r star to be arbitrarily close to 0, or whatever value you want. So this function f is also sometimes referred as blackening factor. Or blackening function. And the reason for this name is that, as I mentioned, this is now called black brane. Actually, in the old days, there was no D, so it was just black pre-brane solutions. And they are black, and exactly as the black hole, for the same reason, in the sense that there is an associated finite temperature, which we are going to discuss more extensively after the break. Okay, let's prepare the ground for the computation after the break. So the next thing that we're going to do is first take the near horizon. For the purpose of analyzing the horizon and the temperature associated to that, this is irrelevant. So whether I keep the 1 here or not, it doesn't matter. But because we are interested in having an anti-de Sitter solution at the end, and we know already, we expect that we will obtain such solution if we drop the factor of 1 here. So I have to take the near horizon. And let's also do at once the Euclidean rotation. So if I do that, let me write the metric and keep it here. Let's also do something trivial. And 3 also define z equal to L squared over r, so that we are back to our coordinates in which the boundary radius is at z equal to 0. So then the metric looks like the following. Notice the plus here because of the Euclidean rotation. X squared 1 over this plus something which we are going to forget about, just the metric on S5. Okay, so Z star is simply a redefinition of the parameter here, R star. And again, when this deformation is not present, which in these coordinates means sending Z star to infinity, you are back to exactly ADS 5 in the Poincare coordinates. And having a finite and non-zero Z star, it's a deformation of ADS 5 in Poincare coordinates. Okay. Yes. Thank you. Yeah.
Are we also making the identification tau positive?
Yes. We are following the same rules because I've done Euclidean rotation, and if you look at this t before doing the Euclidean rotation, if you look at this t z part, it has a horizon really if you are in Lorentzian, and then as z goes to 0, sorry, now in this case as z goes to infinity, well, in this case z will go to some finite. when z hits this value, then this factor goes to 0, this goes to infinity, and you have to make this analysis as I did for the Schwarzschild black hole.
So the claim is that this is a deformation of ADS, but it's not a solution to supergravity.
It is a solution of supergravity. Yes. It is a true claim, yes. So the other true claim is that this deformation breaks supersymmetry completely. I cannot prove this to you here, but it's true. And intuitively, it has to do with the fact that we will see that there is a finite temperature. I have been a little bit sketchy here in the sense that I have not presented I've not told you the dilaton, what it is, the phi from flux, what it is, etc., but everything is deformed in a controlled way, and here I have just highlighted how the magic is deformed. Let's have a break. Shall we start? Yeah. Okay. So now perhaps I don't have to do this calculation in full detail again, but it really follows exactly the same steps as for the Schwarzschild black hole. So we can define a new coordinate rho through z over z star equal to 1 minus rho squared over L squared, so that when z goes to S star, the position of the horizon in Lorentzian signature, then rho goes to 0. So z goes to z star if and only if rho goes to 0. So rho now it's our radial coordinates, and we are interested in studying the behavior of the metric only near to rho equal to 0, which is where all the action takes place. And after some rather simple algebra, one finds that the metric near to rho equal to 0 takes the form d rho square plus 4 over z star square rho square d tau squared. Let's also write the horizon part. So let's focus on the 5D part. Just forgetting the S5 part. So exactly as in the Schwarzschild calculation, that this fixes, now by requiring regularity, that fixes the periodicity of this coordinate tau. And its periodicity, it's by definition 1 over the temperature. So 1 over beta, which is equal to T, temperature is given by 1 over pi z star. Okay, so I could go back to my metric there, and wherever there is z star, insert T. So essentially, T, the temperature, is a parameter of the metric. Now, because this came from the near horizon of a brane, which has a Lorentz invariant, so it has an translation invariance in the transverse space, this remains, and strictly speaking, the horizon here is non-compact because these axes are coordinates in Cartesian coordinates. But then we simply, when we do our computation, we simply regularize this by saying that we write some volume over 3 and think of this as a box. In practice, what we're going to compute next are quantities that will be proportional to that, so we divide by this and consider densities as quantities which are then well defined. So the interpretation of this solution here, it's simply the following. So we're taking n equal 4 superyoung-Mills, and we are just putting this at finite temperature, where we consider our n equal 4 superyoung-Mills in flat space. So at finite temperature will be S1 cross R3. We can also compute the entropy of this, exactly as I was already alluding to here. So the entropy is given by the area of the horizon divided by 4G5, and it's therefore, so A is equal to this factor here. So it's L to the Z star cube times the volume of R3, which is infinite to the cube. maybe I will leave the solution here written down just as reference. In fact, I just wrote G5 in the previous section, let's say. So this area, which is depending on the temperature, I have this G Newton, which depends on G Newton in 10 dimension, and then through L, also in various factors of n. So the entropy at one level is given by, let's put the volume already on this side. So volume over 3. So we have L cube, Z star cube. And then I insert G5, which is 1 over G10 times L to the 5 times volume of this 5 sphere. Times 4. So you see that these worrying factors of 3 and 5, worrying because there will be some quartic root of n, but they combine to give L to the 8, and so the final result is again, as the central charge A and C, exactly proportional to n squared. So that's the first achievement for that. We got n squared, and the factors of GS and LS all cancel out. So what remains is, similarly to the previous computation, we get some 1 over the volume of S5 for similar reason as before. And then we get a factor, which is pi to the 5th over 2, and t cube, right? So the t cube comes directly from this z star cube. Again, since we are really focusing on n equal 4, I simplify the factors of pi from here, and then I get this formula, half pi squared t cube n square. Okay, so what we did compute, and what can we do with that? Namely, can we do some comparison, some checks? So remember, I mentioned, although I didn't really explain what goes into details, but I mentioned that the central charges are quantities which are robust, the anomalies, and so it can be computed. In principle, I'm telling you, can be computed on both sides of the duality and can be matched. Indeed, for the n equal 4 case, remember we got that A equal to C was n squared over 1/4, and that is exactly the same result on both sides of the computation, which can be done independently, and they completely agree. So here, let's recap what are we dealing with. So this is the holographic dual, conjecturally, of n equal 4 super Yang-Mills. Good, so far. At temperature, so at temperature T. Okay, well, not so good at this moment as far as comparison, because we have to remember, we tend to forget this as we go along, but we have to remember that we are at large n and lambda very large. So we had very strong coupling. So this is physically, this is supposed to be dual to a plasma that is studied in some laboratories, where it's a version which starts from n equal 4, but because supersymmetry is completely broken, then it's kind of supposed to be similar to the real plasma in QCD, although it's not quite the same. But in any case, this is something which is at very strong coupling, and there is no technology, there is no computation, as far as we know, that we can do in order to compare this. No analytic computation. Something which is very easy to do, and can be done very simply, is to compute in the free theory. Right? So compare with S over volume in the free theory, free n equal 4 at finite t, at the same temperature T. Let's call this, for brevity, little s, so the entropy density. Okay, so in the free theory, namely at zero coupling, the result can be obtained, and it's just given by counting essentially the degrees of freedom of the free Young Mills and the free boson and the free fermions that are in the system. So S free is 2/3 pi square n square t cube. Okay, should we be excited, surprised, disappointed? So I'm saying we should not really be disappointed, and we should not even be surprised. So we get a different factor. We get 2/3 instead of 1/2. Well, the n square, it's basically coming from the fact that the matrices are n by n, and in the free theory, this is what you're going to get, results proportional to n square. The t cube, it's completely trivial because it comes from dimensional reasons. So the temperature has to have dimension of the mass, which is the same as the dimension of the entropy. Sorry, what am I saying? Yeah, the entropy density. Sorry, the entropy density. This one has dimension of the mass cube because it's divided by 1 over volume. So because T has dimension of mass, then it has to come with a factor of 3. But this computation, in principle, had nothing to do with the computation that we did in the strong coupling. So there is this factor of 4/3 mismatch, which was not present in the anomaly computation, that we got 1/4 on both sides on the nose. So I think I will make some other comment and then leave to you to kind of decide what is the importance or meaning of these computations. The comment that I can make is that we get that S at lambda equal to 0 divided by S, sorry, let's say at lambda infinity, S at lambda equal to 0 is 3/4, which is 75%. And on the other side, in lattice QCD, people have computed this to be, so I am told, of the order of 80%. So then in the lattice computation, you can vary your parameter. You are in QCD, you're not really in n equal 4 Young Mills. But this fact makes some people believe or hope that the calculation that we do in the Young Mills holographically has something to do with what people do in the experiments. So as I said, it is suggestive, but it is not completely convincing that this has nothing to do with the real experiments. Okay, so I really leave to you. You are grown-up adults. You can think about that. Let me say something else, which has nothing to do with predicting results from the Brookhaven laboratories, but is a conceptual point which I want to make. How we can introduce more parameters in our supergravity solution, in our holographic understanding of the thermodynamics of whatever field theory we are supposed to be describing. So if we want to have more parameters, then we have to have more fugacities that we add to our system. So in particular, if we're interested at being at finite charge density, not only finite temperature, but also finite charge density, then we must introduce an associated chemical potential for that. So if the charge density, let's call it J0, then the corresponding conjugated parameter to the thermodynamical parameter, let's call it A0. And the reason why I call them J0 and A0 is because they have the J has to be part of a conserved current, right? So this is part of some Ji in the boundary theory, and it is conserved. And according to the master formula and master concepts of ADS-CFT, then the coupling, well, if you are in D dimension, of this type, then corresponds to the fact that this source, and here the nomenclature, the notation is inverse to what I was using before. J used to be the source in my original notation. Here it is the current, and this is the source. So this is the parameter that one can tune. And this, in the bulk, must extend to a gauge field, which I will call A mu. And this is again a general rule which I mentioned and outlined at some point earlier on in the week, that whenever there is a global symmetry in the boundary, that's associated to a gauge symmetry in the bulk. So that's one of the rules that you have to embed in your head. And this AI, it's the boundary value, so it's the transverse part, and it's the value at infinity near to the boundary of the gauge field A mu. So then you see that almost as the metric, the presence of a gauge field is as important almost as the presence of the metric, because it allows you to deal with symmetries and conserve charges in the boundary theories. And therefore, that, for example, justifies my explanation of gauge supergravity already in the second lecture. So gauge supergravities with abelian gauge fields are quite important for the ADS-CFT correspondence, because they capture the conserved charges of your physics in the boundary. Now, back down to Earth, what are the symmetries of our preferred solution? We discussed that extensively. In our case, the symmetry, apart from the conformal symmetry, the symmetry of S5 is S to 6. So whatever current, whatever U1 gauge field must be some gauge field for some Cartan generators of this S06. So in general, there are 3, right? So in practice, if you're interested in actual deformation of our previous solution, that was a finite temperature black hole corresponding to n equal 42 million mils, then we have to turn on some gauge field which corresponds to gauging one or more of these symmetries here. So then the outcome of all this discussion is that the charge density in the boundary correspond to electrically charged bulk solution, and perhaps I can replace the word bulk solutions with black holes more specifically, if you're interested in finite temperature. Actually, more in general, I could have, in principle, finite density and zero temperature. So the two things are not really necessarily tied together, but if we in a generic situation, we have finite temperature and finite density. So we have a black hole which is also electrically charged. And in the formula, then the gauge field there is A. We'll have to reduce to some A0 dt as for, say, the coordinate z that goes to 0. So that's the general expectation, but it is not something abstract and mysterious. One can easily construct exact solutions which fulfill these requirements here. So I will give you an example. So I will write down a further deformation of the finite temperature deformation of the ADS-5, which takes the following form. So this can be obtained in an effective theory, which is exactly what I wrote a long time ago, namely Einstein-Maxwell plus cosmological constant. And this solution exists, in fact, in any dimension, as ADS exists in any dimension, and as finite temperature ADS exists in any dimension. Also, this modification exists in principle in any dimension, but of course, the main interest will be in 5 dimensions. So let's write the 5-dimensional coefficients. The solution takes this form. Minus f of z plus dx squared plus dz square f of z. So if f is equal to 1, that's just ADS-5 in Poincare coordinates. If f is equal to 1 minus z over z star to the 4th, this is the finite temperature discussed in the previous hour. And the further deformation is this. So there is some constant here, which I don't want to discuss, which reappears here, and there is an extra functional dependence here with the power 6. Okay, so we have 2 parameters now. We have z star, which is 1 over t, and we have mu. And actually, to explain, to justify the fact that this is the deformation that I'm talking about, I have to write down the gauge field, which is given by mu times 1 minus z over z star square dt. Okay, so let's see, when z goes to 0, which is the boundary, this gauge field goes to mu times dt. So if I compare with the general discussion, A0 is mu. So the chemical potential is mu. Good? Is there any complaint at this point or confusion? It's not in my notes, so I don't remember. It's some combination of G Newton and factors of 2. Yeah, it's not important. It's a constant, yeah. So you're completely happy? I derive the solution, define the chemical potential. We can wrap this up. Now, the reason why I'm kind of posing and asking you to reflect is that the immediate confusion that comes to mind is that this constant term is just a gauge freedom. So I can do a gauge transformation and just suppress it. So when I go to z to infinity, I get 0. Or I can just add whatever I want and get another parameter. Instead of mu, I will have another parameter, mu tilde. But there is no such a freedom. Although it looks like there is this freedom, there isn't. And the reason is that you have to ensure that your solution is regular near to the horizon. So for the metric part, the discussion that we did earlier is completely unchanged, almost completely unchanged. It's just that there is a different factor here to consider. This is subleading, so it doesn't really matter. So there is a temperature that one can fix, and it's given by T equal 1 over pi z star, what was exactly what we found before, and then a modification which is 1 minus c mu square over 2. Okay, so the temperature itself is affected by mu, so it's really a combination of the parameter z star and mu that gives the temperature. But mu is really interpreted as the chemical potential from this formula here. And the reason why this cannot be changed is that you have to study what happens at A for Z going to some Z. Now I have to put some hat here, where this function goes to 0. Okay, so now the horizon is slightly moved because it's this function that goes to 0. So it has a slightly different 0. But nevertheless, you have to study what happens here. And I think here I should have put a different parameter. In any case, you have to make sure that A goes to 0 when you go near to the horizon. So that fixes the fact that you need this constant term here, because otherwise this would go to some constant times dt, but dt in Euclidean is like d phi, the angular coordinates, and that's not well defined, right? So at the origin of R2, the angular coordinate is not well defined, so a one form which is d of this angular coordinate is not well defined. It's basically singular, so you have to require that whatever multiplies that angular part goes to 0. And that is ensured by adding this constant, and that fixes uniquely that constant. Okay, so then we have our chemical potential, we have our temperature, we have our volume, and then we can compute all the thermodynamical quantities of interest by using the rules of thermodynamics. So the only thing that one has to just pause and notice is that because we are at fixed mu, then this fixes the ensemble, and we are in the grand canonical ensemble. So in the grand canonical ensemble, just recall from your statistical mechanics lectures, we have this relation where here I write n as charge density or particle density. And that is related to the partition function through z of the field theory equal to e to the minus beta omega. Right, so this is all field theory. And then the ADS CFT correspondence comes in. So this equality is rather, let's say, master formula. So the master formula tells us that this is equal to e to the minus s supergravity. One possible confusion, this is the entropy. It's not the action. Unfortunately, they have the same name, but two completely different things. And so from here, we conclude that our thermodynamic potential of the grand canonical ensemble is going to be given by T times the supergravity action. And the supergravity action will be a function of the external sources, which are, in this case, mu, and of course, T is one of the parameters that we can tune. Well, and of course, there is also the volume, which is one parameter. So I leave also this as an exercise to take this, plug it back, and you can check that. So in the last 15 minutes of the lecture, I want to consider the other case of heating up ADS, which is starting from ADS in global coordinates. So there is a different physics associated, I mean different aspects of the physics of n equal 4 EM mills at finite temperature. And here, because we are in global coordinates, as already explained a few times, it means that our boundary theory is defined on R, which is the time direction, times S3. So we are really putting the theory in a complex space, which is a bit like putting in a box, but do it in a more gently, putting on a 3-sphere. So we can do that independently of any temperature. So this is a possible direction. One could study this with supersymmetry, for example, and there is some very long and interesting story. But now we add finite temperature. Okay, so as soon as we do that, then we know that we end up at, in the theory, in Euclidean. And then we compactify the time direction on a circle of radius beta, and the S3 remains an S3. So this is an S1 circle. So this is a boundary theory. It lives on this space. So here is our space here, right? And then we have to find a solution that has this space as a boundary. So it is like a called fill-in problem. You have to fill in this boundary. It's like you're given the shell, and you have to find, oh, this is not, what, somehow what fills is in. And the master formula of the ADS-CFT, I'm going to rewrite by highlighting yet another aspect, which I have not done so far, is that the partition function of your theory defined on S1 times S3 is equal to the sum over some I of Z supergravity xi. So this seems to come out of the blue. Why did I not worry so far? Well, I should have always worried. So the true statement, the correct statement, which Witten again pointed out, is that if you apply this correspondence and you're thinking of the right-hand side as a saddle point evaluation, then you have to sum over all the possibilities. And there could be many. There could be 1, 2, 3, maybe even more, right? So xi here are possibilities for these manifolds. So, right, in principle, this is the formula that you have to apply, always, in any situation. Now, typically, and for all the examples that are known so far, including some subtle ones that were understood more recently, when you have supersymmetry, then there is a unique filling, and you don't have to really worry about that. When you don't have supersymmetry, then this uniqueness is not known to hold, and in fact, there are examples, including the one that I'm going to just mention now. So examples in which the manifold inside is not unique, and in my case, there will be two cases, two options. But as I said, they are not really options. It's not like I have to think hard and decide which one of the two is the correct one. I really have to sum over both. So I give you the explanation of what are the two cases. X1 is called thermal, in some arbitrary labeling, thermal ADS. I have to speed up a little bit. And the metric is simply the global ADS metric with the weak rotation, so Euclideanized. It looks like the black hole matrix that we discussed before, just with one important difference, or maybe two important differences. One difference is that here there is no minus, so in fact this function, this r, can go to 0, but that's just maybe just an artifact of the coordinates. The physics has to do with the fact that when let me finish this so I can write this in any dimension. Okay, so when r goes to 0, this part of the metric, you see, it does not go to 0, just goes to a constant, and this part goes also to a constant. So in fact, you can study for r going to 0 the topology of this metric and how this metric looks like near to the origin is that of S1 times R4. Right? So the R4 comes from well, let's do this concretely. I don't have to do the dimensions. So the R4 comes from the three-sphere that shrinks smoothly, and then here this is just the coordinate dr square. In fact, you don't have even to do any coordinate change. It's trivial from these coordinates. So the physical consequence of that is that the temperature is not related to any parameter of the solution. And that's kind of good news because there wasn't really any parameter. Well, there was L, so in principle it could have been related to L, but it's not. So the temperature T, or the radius of this tau beta, are free parameters, as well as this L is a free parameter. Well, free, but then of course in the solution given in terms of n, alpha prime, and so on. So a question for everyone. Can I take a few more minutes, although it's almost lunchtime? What, is there any strong objections? Honestly. At most 5, yeah. Okay, let's say at most 5, according to that clock there, as a reference, right? So that's one solution. Let's say, what is the other solution which I claim exists? The other solution is called Schwarzschild ADS black hole, and in similar coordinates, it takes the form f of r d tau square plus 1 over f of r dr square plus r square ds square of S3, where f of r is one of these polynomial functions of r, and it's 1, not surprisingly, minus some mu parameter r to the, here I have d, so this is d minus 2, it's 1, and then r square over f square. Okay, so the horizon is by definition at f of RH equal to 0. That defines the position of the horizon. So this is now a cubic equation, and this is the largest root, right? As you come from infinity, the first time that this vanishes, that gives the horizon. The other inner roots are not relevant. Okay, so there is a slightly more sophisticated computation to do to check what is the relation between the temperature, namely the periodicity of tau, and the parameters mu and L, which involves, it's a nice exercise actually, so no, I don't have time to do this now before lunch, but I leave that to you to do, and if you have problems you can ask me. So one can determine that by doing exactly the same computation, which I've repeated now twice, the temperature associated to this solution is in general 1 over 2 pi absolute value of the derivative of f, this f, evaluated at the horizon divided by 2, and after doing the nice algebra, there is a formula which is 4 pi r horizon L square times L square plus 3, no, these, okay, now I lost track what was my D here. D is 4, okay, D is 4, so I may have written some wrong factor somewhere. So this is 2, and this is 4, R horizon square. Right? Okay, so that's the temperature. It's related to the parameters of the theory, and R horizon is by definition then related to this mu and R square. And as a function of the parameters of the theory, or rather from here you can see it's actually a non-trivial function only of the radius of the horizon, then one can see that this function has a minimum. So there is a minimum temperature which is given by 1 over 2 pi L, and I suddenly write the formula for D because it's quicker for me than to plug D equal 4. So far D equal 4, but everything can be set for general D. So that for T larger than this minimum value, both solutions exist. So both this one solution exists, obviously, and the other one solution exists because that exists for any temperature. You can, it's a free parameter. That's what I said. You can really choose it to be anything between minus infinity, well, 0 and plus infinity. Whereas this one exists only for T larger than T minimum. But when both exist, you have to apply the master formula and sum over both solutions, right? So you get that your Z is equal to e to the minus s of x1 plus e to the minus s of x2, right? And it becomes clear what you really have to do by taking out one of the two in a factor and writing this 1 plus e to the minus s x2 minus s x1. So then suppose that s, in this case, suppose that s of x2 is larger than s of x1. Here s is the onshell action. So if this is true, if this inequality holds, then this is e to the minus something positive, so it is exponentially suppressed, very, very suppressed. In particular, it would be suppressed with factors of e to the minus n squared, if you follow through this, the factor of n, with respect to this coefficient. So essentially, you can neglect that. It's really a very, very heavy suppression. And Z you can identify with e to the minus s of x1. On the other hand, if the opposite is true, that this inequality is reversed, then by simply rearranging the terms, you can see that s of x1 is exponentially suppressed, and here you get e to the minus s of x2. So then it means that according to which temperature you are, then there is this prevalent dominance of one or the other, and this can be determined by computing explicitly the difference of the on-shell actions, which I'm going to write. So s of x2 minus s of x1 is equal to 1 over t r horizon to the d minus 2k square. This is the G Newton coefficient. Then there is some volume of s minus 1. And then here is where the important sits. 1 minus r horizon square divided by L square. Notice that to do this computation, the divergences will cancel out, so you don't even have to do a lot of sophisticated holographical normalization to compute that. And you see that at RH equal to L, then it's the place where you have this phase transition. So RH equal to L corresponds to a temperature, and the temperature is not written in my notes, but it doesn't matter. You can read off from here. So when RH is equal to L, you get a temperature at which you get this phase transition between one phase where one solution dominates and the other phase where the other solution dominates. So this is called Hawking-Page phase transition. And the interpretation of that in the dual field theory, where you have your field theory n equals 4 super Mills put on S3 times S1, is in terms of a confinement and deconfinement phase transition. But obviously, we will not have time to speak about that in more detail. I just wanted to highlight the physics. So this fact of this summing over manifold and possible phase transition is really a feature of the ADS-CFT correspondence, which I wanted to highlight. So thank you for staying 5 minutes more. The good news is that I've done everything which I wanted, so tomorrow I can talk about n equal 1 supersymmetry, which some of you might like. Okay, see you later. See you at lunch.